Now this first section is not actually in the notebook, but we're going to be doing a lot of reactions next class. We're actually going to do six different reactions, and it's going to be at your station. So you're going to have one station, it's going to be one reaction, then 5 minutes later you rotate to the next station. So in about a half an hour, you'll do 6 different reactions. They are everything from just pouring 2 solutions together, to lighting Bunsen burners and making things catch on fire. It's the full spectrum, but it is going to be very dangerous. There's parts of it that you can get hurt. So we're going to have to go over some serious safety things ahead of time, and we need to really pay attention. It's also going to be one of those where I'm going to be like, you messing around, you're done. No slack. But what you might see, you're going to observe a lot of different things as we do this. You might see color change when you do that. Some of those reactions. That's good evidence of a reaction. You might see a precipitate form, and is that a new word for us? Precipitate in this form? Yeah. Okay, so a precipitate is a solid from 2 solutions. So if we have 2 solutions, 2 things that are dissolved together, we mix them together, we see a solid be formed. We call that solid a precipitate. Another thing we might see is you mix things together and you see a gas formed. That's great evidence that there's a reaction taking place. And the fourth one's easy to see if you have a thermometer, but not easy to see if you're not touching it and don't have a thermometer. But anytime you mix things together and there's a reaction, heat is exchanged in some way. There's never zero heat change. There's always some heat change. It might not be observable, like if you're holding it. You might not observe it in your hand, but there's always some heat change, as heat is either given off by the reactants or absorbed by the reactants. So as we do the reactions next class, you're going to make a lot of observations. You need to record those within the lab. One thing, though, you might not observe is the weight. If you weighed the reactants and then weighed the products, they should be the exact same. It's not like we're creating or destroying mass when we do these reactions. When you do chemical reactions, you just rearrange the atoms. And we have some great things today to look at to kind of help you see that. Yeah, question? So the question is, what if you have a reaction, a bunch of gas is given off? Well, hopefully you've got a system or something to contain the gas in, so you could weigh it before and afterwards. When you collect it in a bottle, and the bottle needs to be evacuated, be a vacuum first, have the reaction occur in a vacuum, and therefore the gas would fill the vacuum, so you wouldn't see any change in the weight on the scale because the gas is filling that empty space. So it's hard to do. You have to have some sophisticated equipment, but you can do it. No, because there'd be no oxygen, so you can't have a fire there, no. And this really kind of goes into today's thing. We're going to talk about why is the mass conserved? Why is it all the same? Well, we're talking about reactions now. We've moved on from writing equations to actual reactions, which is why our labs get more complicated and from your perspective probably more interesting. We're going to have reactions, and that means that you start off with something that we call reactant, you mix it together, you light it on fire, you do something to it, and then those elements rearrange and make new products. So we always start with reactants, and we always end up with products. And what's been found is that there's certain ratios that always pop out, and they're related to moles, and moles are hidden in here again, but we're not going to be doing masses and moles again yet. That's to come again later. But whenever we have an equation, there's certain things we could say. Like here, we could say CH4 reacts with oxygen. What do we say for the arrow? Yields or produces. And it's a symbol that to separate the beginning from the end. So this is the beginning of the reaction, this is the end of the reaction. And I had a question earlier, are there always 2 things reacting to produce 2 things? No, you could have any combination of things. You could have one thing breaking apart into a bunch of things, or a bunch of things combining together into one thing. But the separation of the 2 sides is the arrow. It kind of separates the reactants from the products. The main thing we're doing in this chapter, though, is make sure the 2 sides are balanced. So I'm going to use a little T-table for right now. Here's the reactants. There's the products, and there's my T-table. What are the elements in this reaction? Yep, carbon, hydrogen, and oxygen. I'm going to go to you. All right, sir? How many carbons are on the reactants side? Just one. How many are on the product side? Just one. So the carbons right now are balanced. We started with one, we made one. What about the hydrogens? 4? Well, if there's only 2 over here, we've got a problem. We need to balance it. What should we multiply this by to get it to the right value? So we're going to multiply it by 2. And this is the big thing we're doing. And we're going to put a coefficient. We're going to put a coefficient in here to signify that we're multiplying the water by 2. That doesn't mean, that means we're making 2 waters. So it's really CO2 plus H2O plus H2O. But we're kind of being lazy. We're not writing every water down. We're saying, and there's 2 waters, putting it in front. Now, how many oxygens are on this side? See, there's already a 2 in front. Yeah, so it's 2 times 2 there, isn't it? It was already a coefficient to help us out. So it's actually 4. And then over here we have 2 plus, yeah. I'm going to do it like this, 2 times 1, all right? Because you're trying to simplify it too quickly for me right now. So it's 2 times 1 plus 2, which is also 4. So is it balanced right now? That's going to be our goal. Our goal is to get the 2 sides equal, because if you start with something like a carbon atom, you have to finish with 1 carbon atom. You start with 4 hydrogen atoms, it needs to finish with 4 hydrogens. 2 oxygens, 2 O2s, there's O2 and O again. It needs to add up to the same number of atoms on both sides. And then we have a little visual diagram of it here. You can see the carbon atoms, there's 1 on each side. The oxygens are moving around all over the place as they get all rearranged. And the hydrogens are over there now, but they're split apart. That's what happens in a reaction. The pieces break apart and come back together in a new way. Usually the new way has less energy than the original way. And this type of reaction is actually a combustion, it's the burning of methane. Questions so far? Stop this one.